In this video, I'm going to show you how to get started with arrays in assembly language programming on the Raspberry Pi. I'll show you how to allocate an array, how to read and write from the array, and how to do traversal. We're going to be using the same GitHub repository that we've been using in all the other demonstration videos. That's github.com/cmcmurrow/CSE2312. So when we load up our repository, we're going to check out the examples folder, and we're going to be looking at array.s. Now when we load array.s, we see a typical looking assembly language programming file. Basically we have the global section, we have our main function, we have other procedures that we've defined, and then we have the data segment. The main difference here is what happens in the data segment. So up to this point, when we've been using memory, we've been using the stack through push and pop. In this example, we're actually going to be using, or rather declaring, a contiguous block of memory in the data segment to hold our array values. So by definition, an array is a continuous block of memory that has a bunch of elements that have basically the same type to those elements. So in this particular example, we're going to be using words as our element. In other words, 4-byte variables as elements in an array of 100 integers or 100 words. So we basically have to start out using this bealign directive, and then we have our actual array definition here. Now in the data segment, I have 4 elements. There's the printf string and the exit string. These are just the formatting strings like what we've been using before in our printf and scanf examples. The array definition requires 2 lines and is actually done right here. So bealign for, as I said before, we're going to be having an array that stores word variables in it. And we know that on ARM assembly, we have byte addressing. So in other words, one word of information is 4 bytes. Therefore, we need to basically align our array to 4-byte memory locations. So specifically what this bealign for is doing is it's saying the next instruction or the next piece of memory that I declare after this directive here needs to start at a memory location that is divisible by 4. It needs to be aligned to a location that's divisible by 4. This is because if you think about it, if we're going to declare an array of 100 elements, we want each one of those elements to have an individual address of something that is divisible by 4. The reason is because if it's not divisible by 4, then 1, 2, or 3 of the bytes within that individual element will be partially stored in the array before or the element before or the element after that particular location. So we would expect that each one of our elements to basically have an individual address that is divisible by 4, and that the actual starting location of the base address of the array should also be divisible by 4. That's exactly what the bealign for directive ensures. So then we have the next line, which is a label A, and then I have dot skip, and then I have 400. This is where the actual array is being declared or being allocated. So A is the name of the array. This is going to just be the label pointing to the array. Dot skip is saying I want to skip forward n number of memory locations, and I'm providing a value of 400 for that. So we want to store word variables or integers, so 32-bit pieces of information in our array. We want them to be stored contiguously. So each memory location will be 4 bytes long, and we want there to be 100 of them. Therefore, 4 times 100 is 400. So these 2 lines are all that you need to actually declare the array. Now we're going to look back up in the actual main procedure in our function and see how we iterate through the array. So what we're going to do in this example is we're going to have a write loop. So we're going to iterate through the array that we created in the data segment. We're going to write the address of each element, the actual memory address of that element, into that memory location so that each element is storing its address in numeric form as its value. So we're going to write that into each of the 100 elements. So basically we would expect that each element will contain some value that is its address, and the element following a particular element will be the value in that previous element plus 4, because we know that each element in the array is 4 bytes wide. So this is the write loop that will achieve that. So let's take a closer look at this. So we're going to actually have R0 as our loop control variable. That's basically our int I that will iterate through the array. This is my check logic for my for loop. So basically, I'm going to compare R0. That's what I'm going to be incrementing every time to 100. If it's equal to 100, I'm done, and I'm going to branch equal, or branch if it is equal to write done. And that's basically the label saying that I don't want to iterate through this write loop anymore. Toward the bottom of this write loop, I have the actual incrementing of R0. So this would be the I++. And then I have a branch back up to write loop. So these two lines and these two lines are all basically loop control logic. So the actual logic or the instructions that are actually taking us to the array are these 4 lines here. So I have a load register into R1 equals A. That's saying that I want to store into register R1 the address that's pointed to by label A, because that's going to be the base address of my array. So now at this point, after this is executed, R1 will contain the base address of the array. Then I'm going to do a left shift left, storing that value into R2, whatever is in R0, and I'm going to shift that by 2. So R0 is our int I, or our loop control variable. So that's going to be the index that we want to actually visit in each element. And we know that the elements in our array are 4 bytes wide. Therefore, if we want to access the, let's say the third element in the array, then we would actually want to take that, it'd be int 2, I would equal 2, because the array started at 0, 1, and then 2. We would want to take 2 and multiply that by 4 to get 8. And that would be the offset that we would have to apply to the base address of the array to access the third element in the array. So that's exactly what's happening here. You have a logical shift left from the loop control variable, or I, which is stored in R0. We're going to shift that left by 2, which is going to multiply it by 4. And then we're going to store that, that result into R2. So at this point, R1 has the base address of the array, and now R2 has the offset of the element that we actually want to access. So if we actually want to get to that target element, we have to add the base address of the array to the offset. So we're going to store into R2 R1, which is the base address of the array, and R2, which is the offset, and we're going to store it back into R2. So after this line is executed, R2 will now have the individual address of that element in the array. So then I'm going to do a store operation, and I'm going to store into memory location R2, which, remember, at this point has the actual element address. It's the offset plus the base address of the array. And I'm going to write the value of R2 to that location because I want to print it out later. So basically the address of the memory location that I'm visiting, I'm going to store that numeric address into that same location just for printing later on. So you could here, whatever you want to write to the array, you'd replace R2 here with whatever register contained whatever piece of information you wanted to write. It could be R7, R9, whatever. So after we've completed that loop, then we're going to do a read loop. So we're going to do basically exactly what we did before, except instead of writing, we're going to read and we're going to do a printf. So we have the two loop control logic lines here, exactly the same as before. And then we have the two loop control variable incrementing and branching back up to the next iteration of the loop lines here. These are exactly the same. So this block here is all the stuff that's different from above. So actually, these elements are all the same. So remember, we're going to compute the address of the individual elements of the array the same way that we did in the previous loop because we're accessing the exact same array. So we're using R0 as a loop control variable. R1 has the base address. These two lines will store the offset into R2. And then the add will actually put the full address of the element into R2. And the load register into R1, whatever is at address R2, is going to actually store whatever is at the memory location R2. In other words, this is the address of the array element we're trying to access. And it's going to read that and load it into register R1. So this is where the actual read operation is happening. After this line is executed, R1 will have the value in the array that we're trying to access. So it'd be A at location I or whatever. Then we have these lines here. So we have 3 push operations. We have a couple of moves, a branch link, and then we have 3 pop operations. This is purely just housekeeping for the printf function because we want to print the result here. So we could delete these lines that I have highlighted and our code would work 100% fine. We would actually do all the array reads here. We just want to be able to display them for demonstration purposes. So because we don't know if the printf function is overriding R0, R1, R2, it actually is overriding R0 and R1, I believe. But because we can't trust the printf function to not destroy those variables, also R3, we're just not using it right now, we're going to go ahead and push those 3 variables to the stack because we're going to need them later on in the next iteration of our function. We don't necessarily want to lose them. So we push all 3 registers, and then our printf function, we're actually going to print the index of the array that we're visiting, the logical index, in other words, an integer 0 through 99. And then second, we're going to print the value that we read from the array, which is going to be a larger number, a memory location. The printf function is going to expect the index to be stored in R1, and it's going to expect the actual array value to be stored in R2. So we actually need to do a little swap here, but we're not actually doing any array access logic here or anything. This is just purely for the printf. So then we move those variables around, or those register values around, then we call printf, and then when we're done with printf, we assume that R2, R1, and R0 have been destroyed by printf or overwritten. So we will restore those, we'll pop them off of the stack, which will make sure that we not only restore those values, but make sure that we don't get a stack overflow. And then we do the incrementing of the loop variable here. So this is basically how the entire example works. So let's go ahead and run it and see what happens. I've already got it queued up here on my Raspberry Pi emulator. So I'm going to go ahead and assemble array.s. And then I'm going to execute it. And you can see here, it's only displaying the 77th through the 99th operations that occurred. That's because I can't scroll up, but it actually did iterate through all 100 elements of the array. It stored in each one of those elements the actual memory address that it was reading to as a numeric value. It stored that number there. And then we did the same iteration, except we read the values and then we called them through printf. So with this example, this basically shows you how to do everything that you need to do to declare an array, how to iterate through an array, how to access a particular element for reading, and how to access that element for writing. So I hope you found this video useful. As always, please like or subscribe, give me a little thumbs up on YouTube, and definitely comment below if you have any questions. And good luck.